professors, doctors, thanks so much for joining. I hope you enjoyed the short lunch we have. My topic is urbanization and climate change effects on urban drainage performance, and I selected a case study of sustainable urban drainage, or SUDS, in a risk area in the city of La Paz, in my home country, Bolivia. So I would like you to watch this occurred in 2002. It was the hardest flooding that
Luego a las
we experienced so far.
14:40, el granizo cayó en todo el
Se ha producido en el último
And
siglo
this
en la
one
ciudad de La
was
Paz.
a
Se
landslide
puede
in
apreciar que la caída del
2011.
cerro ha provocado que la
Both events were closely attributed to excess of rainfall and stormwater management issues. So the aim of this research was to assess the impact of climate change and urbanization on the drainage systems performance using stormwater management model developed by the EPA of the United States, which is an open source software. And it's also a simulation one that included improvement alternatives of an area of interest in the city of La Paz. The study was guided through 6 objectives, which I summarize here. It's analyze geospatial data, elaborate a disaster database, analyze precipitation data, select an area of study based on these 3 first objectives, and then assess the drainage performance in this selected area to finally evaluate the application of SUDS, or sustainable urban drainage systems. Regarding the background, as you can see from this picture, La Paz settles on the slopes, usually on the slopes of the surrounding hills. So it's quite a complicated topography, also similar to other cities in Latin America. And it has more than 1 million inhabitants. It conforms part of the metropolitan area with its neighboring municipalities like El Alto, which is where the airport locates. The altitude varies vastly between 3,000 to 4,000 meters above sea level. So as you can see in the purple area, that's where it starts going down. It locates in the valleys of this mountainous region. And this, of course, involves some risks because of the steep slopes and the geology conformation. It elevates the vulnerability, and the municipality has created this map, which is the risk map, that helps assess the public administrators how to deal with these conflict areas. The ones in blue, and color mixed blue and red, actually are the 36 highest risk zones, which I chose one of those for these studies. And the administrators try to regulate the urban settlement through a land use regulation, and this is the land use map that they utilize to do so. The city is divided into, the municipality is divided into 9 macro districts, 7 of which are urban, and these are the ones that the study focused on in the first stage. And as I mentioned, the country itself, Bolivia, is highly vulnerable. This index developed by the University of Notre Dame ranks Bolivia in one of the lowest positions, second to last in South America. And our partner countries from Spain, Finland, and the United Kingdom, as you can see, rank 3rd, 11th, and 26th. So what can be a solution to improve the stormwater management in La Paz? Is through SUDS. There are many options. Some of our colleagues already presented, for example, green roofs, but also it can be filter strips, pervious pavements, bioretention areas, and the ones you see in this slide. So regarding methods, I want to quickly go through these. It utilizes this framework. As you can see the image, I'm just going to explain at the core. It's the simulation, which utilizes different inputs. For example, the land use maps from satellite imagery, precipitation scenarios from different academic research and precipitation data, and of course a digital model that was built reflecting the infrastructure conditions for this. The data sources vary from satellite imagery, Landsat, QuickBird, and others, and also data was obtained from different public entities, which, for example, GAM-LP is the municipality, CENAM is the hydrological service, and EPSAS is the stormwater company, and also academic research. So going to the results and discussion, the first result was comparing the urban sprawl or the evolution between 2000 and 2020 to see what was the settlement patterns. As you can see, most of it in this, well, it looks yellow in this slide, is bare soil, and followed by urban built-up areas, which in these 20 years has evolved quite a lot, as you can see in these comparative images. For example, bare soil has decreased 18% in this 20-year frame, while green areas and forests combined have decreased almost 5%. And the most highlighting change was in urban settlements, which went up at almost 37%. However, compared to the population rate, this almost doubles the one as the built-up areas. So that aimed to infer that there was high pressure for housing, and that can, for example, influence on medium-rise or high-rise constructions, as well as horizontal expansion. So the second step was to build up a disaster database. 16 incidents were cataloged and compiled from news media, which was the source, and most of these incidents happened in District South or Sur. As you can see from the chart, you have more than 16 incidents there, but it's because some of these incidents are shared between these macro districts, between these 7 macro districts. However, the most recurring type of event was flooding. As you can see, 9 times out of those 16, and as you saw in the video, the worst ones happened in, well, 2002 with the flooding and 2011 with the landslide, which one of the reasons was provoked by not only the stormwater infrastructure failure, but also to the urban settlements on risk areas, and of course the soil stability, sorry. But what does the scientific research says about Bolivia's precipitation? Well, they aim towards two points, that we're going to have extreme events recurring in the future because of, for example, El Niño or the southern insulation or La Niña, which is going to cause, of course, more flooded areas. We already had in 2016, 2018, but we're also going to go through more water scarcity, which is going to create droughts, and of course glacier retreats, which might affect the water provisioning. So regarding precipitation, in the precipitation analysis, I obtained records from 10 stations. In the graphic, you can see that I actually found that some of these peak values are related to the extreme events that I just mentioned, 2011, 2002, which was reflected in the records of precipitation. The rainy season goes from December to February, opposed to here we have summer there. However, the rainy months go from October to March, as you can see from this graph. So I divided by these rainy months, and that's called the dry months, the trends, to check up if there was any trend actually. And to compare that, I utilized a Mann-Kendall test, which is quite widely used for environmental and extreme cases, which was confirmed. And this was for average yearly trend. But then with the same data, with the data of maximum precipitation in 24 hours by season, the trend was also confirmed. However, this was a 90% confidence level, and this means that in the future, there's a 90% confidence that we might have more extreme events. But however, this cannot be directly attributed to climate change. So based on these 3 first components, the disaster occurrence, the urbanization patterns, and the precipitation, I selected an area of 12 hectares in the District Sur or South. And you can see from this image, this one is a supervised classification map that I made of 2003 with high resolution images of satellites that transform into, of course, more urbanized, more structured, developed settlement. So this involves more urbanization, more imperviousness. This is the imperviousness percentage of this whole area divided by subcatchments. That these can involve higher imperviousness, higher runoff. As you can see, comparing 2003 with 2020, the increase was of 40% in average in this area, this study area. And this is the swim model. These are the 61 catchments. On the left is 2003, and on the right 2020. And as you can see from the color grading, they went higher, nearly between 54% and above. So the simulation was also, the infrastructure, or was, I did a solidification in this area because, as you can see from the pipes, the triangles are different discharging points. And the area had 61 subcatchments, 65, 63 utility holes. So two scenarios were run. The first one was for land use cover of 2003, 14, and 2020, just to see what happened due to the urbanization. And the second one involved the land conditions 2020 plus a factor of plus minus 20% in precipitation because of the research findings. So the results show that, of course, after 2003, there was a higher increment in the peak flow compared to the one of 2020 with 2013, as you can see in the curve. And the same happened with flooding. There was almost no flooding in the 10-year return period in 2003. However, this was present for the next years. This involved overloading in the infrastructure. For example, in 2003, you would have 2 units of surcharge pipes, but this goes up to 10 in 2020. That was just for urbanization. So the scenario 2, including the increase and decrease, rainfall increase of 20% and rainfall decrease of 20%. There's also changes in flow and in peak flooding, And you also have increments, of course, if you increase the rainfall, you will have more overloaded elements in the stormwater network, and you have a decrease if there's less rainfall. However, even if with decrease of the rainfall, you would still have flooding and other overloaded elements or surcharge pipes. So because of this, as you can see from here, in the zone 3, these all elements are usually under stress or under failure. That's why I selected the zone 3 for 9 groups and 8 streets to see what would happen if you implement those and how the system would respond. And the key results are these, that with green roofs, you will have the decrease in flowing, which might be quite low value, but in flooding, you will have up to, on average, 22%. The surface was above 1,000 square meters, and the efficiency is the one that you're seeing. However, the previous pavement have better results for using these values, but they occupied more space and because of that, they had a less efficiency of 0.08 liters per square meter. So to finalize, I have 2 more slides. The discussion, the findings, the research confirms, thanks so much, the other authors' findings that actually SUDS are capable of reducing peak flow and peak flooding, and they, of course, have other benefits, collateral benefits, because of their implication. And the SUDS, however, even with the reduction of precipitation due to climate change, the system might still overload in the future. The challenges, according to 2 interviewees that I had showing these results, are that there can be institutional, monetary, planning, and risk management barriers that need to be overcome to maybe implement these type of solutions. And 2 of the main ones are related to public budget and technical norms, or the lack of technical norms and regulations. However, the limitations were data assumptions regarding, for example, the design storm. That means the duration that I introduced into the program to simulate this, and also the green roofs and permeable pavement conditions that were assumed as sufficient. And also regarding, for example, precipitation measuring and assumptions regarding potential changes in rainfall source. Okay, to conclude, the potential overload of the drainage system was demonstrated by the simulation. Flooding and flow can increase the risk in areas prone to stability issues. So this water that comes out of the system might be affecting the ones that are in slopes nearby they might crack or create soil instability. So that's also another risk. The utilization of SUDS can enhance the performance, of course, and reduce the overloaded elements. However, you might still experience surcharge, pipes, or flooding. The current technical regulations do not include criteria for SUDS, for example, house development regulations or infrastructure regulations are not including currently these types of solutions. So there's a lack of technical and legal instruments. This simulation was seen as quite valuable by the interviewers, so it can work as a guidance for practitioners and public administrators, as it includes criteria for addressing potential risks due to drainage network performance. Well, the results need to consider the limitations, and on-site collection of data would enhance the results. Thank you so much, and I'll be open to questions.